All right, everyone, welcome to another week. We're going to get into something a little more elaborate. We're going to be talking about, you got it, computer systems and fundamentals. So last week we looked at some of the basic electrical applications, and this week we're going to actually see how we use that electricity or manipulate it to perform certain actions that we want within the automobile. So this week, we have some main objectives that we want to focus on. We're going to take a look at inputs, how those inputs are processed, and then what the final outputs are. We're going to talk about the input sensor technology as well as the output device classifications that are there. And we'll summarize how those computers, sensors, and actuators are typically located on a vehicle. And all of this is obviously in an effort to properly prepare you for the ASE exam. Okay, with the automotive computer, keep in mind this is a complex set of electronic circuits, and they receive input signals from sensors, and it produces pre-programmed output signals that actually control actuators. You can think about this much like when you touch something that's maybe hot, your brain interprets that and you react and you pull away from it. The same thing might happen on a vehicle, and the computer is there to monitor these systems. Numerous advantages occur when we're dealing with computer systems. So one of the first things that computer systems allowed for was to compensate for mechanical wear. Where years ago, what we'd have to do is go in for actual manual adjustments. The computers can compensate for that. And it doesn't have any mechanical parts, so there aren't parts that can go typically bad because they're not moving and they can't fatigue. They can react really quickly, and they help reduce our fuel consumption and their emissions, which in turn helps us increase horsepower. It also reduces weight that's on the vehicles. We now have onboard diagnostics so that we're able to hook up computers to generally give us an idea of maybe suspect components that have failed. These computers allow for increased occupant comfort and convenience. And we notice this because of our ability to connect our phones and different apps that we now use, maps, for example, and guidance systems. And all of this is in an effort to reduce some of those distractions, which in turn improve passenger safety. Computer systems generally have three different stages. And they can be broken down into other subsystems, but we're going to be looking at inputs that include the ability for us to have sensors on the vehicle that monitor conditions. This in turn relays information to the ECM, or the engine control module. Those inputs are analyzed, they're processed, and those inputs that are received by the ECM decide on what operation should be adjusted and issues commands to the actuators. Those actuators or outputs controlled by the ECM act on commands issued by the ECM and cause various functions to change. Here's a good representation of a layout that may be on a typical automobile. On the left-hand side are the inputs with the ECM in the middle. These inputs feed the ECM information, which in turn operate the outputs on the right side. Take careful note of the names of some of these sensors so that you're familiar in the future when you're reading through whether they're an input or an output. The computer signals that we typically deal with use voltage variations over very short periods of time. And sometimes you'll actually hear the term oscilloscope because we end up using these scopes to capture those signals because they happen so fast. Otherwise, we wouldn't be able to see the actual voltage changes. They're specific and they're arranged in methods that have logic that are involved to tell certain components whether to turn off or turn on. There's two different types of signals that are available. There's digital signals, which are on-off signals, and then there are analog, which gradually change in strength. Here are some images that describe the differences. With digital, it's either on or it's off. You either have 0 or 100% of the available voltage. With analog, we can vary within that 0 to upper range, and whatever that range may be. When dealing with these computer signals, we have some terms that we typically use. You'll hear the term pulse width or signal frequency. This is how fast is that voltage signal changing over time. And as computers have gotten better, those signals change much quicker. There's also signal amplitude. How much voltage is present in the wave? So different voltages, whether it's a 5-volt or 12-volt system, will have a different amplitude. The duty cycle is the percentage of on time compared to the total cycle time. So in other words, how many times does it cycle within 1 minute or 30 seconds? Here we see the inputs and outputs, and we need to start to understand that as vehicle sensors change physical condition or physical movement into some kind of electrical signal. In other words, when you turn a knob, some kind of reaction takes place. How do we do that? Well, we use different inputs. You can see them listed here on the left-hand side. There's variable resistors, there's potentiometers, there's your general switches, there's voltage generators, very similar to maybe like a battery or even an O2 sensor is known as a voltage generator. And then there's magnetic pickups. These are all sent over to the ECM, and these sensors can be found anywhere on the vehicle. And then in turn, we have some kind of output that occurs. And in this case, you can see on the right-hand side for outputs, we usually use things like DC motors, solenoids, maybe a relay. In some cases, it's a display unit, right, like a monitor. And then sometimes we have computers that inform other computers about what's going on in some other system. And these are what we get into later on that you'll learn about that are networks. These sensors come in different names. There's what we call active sensors, and those active sensors, those produce their own voltage internally. Then there's what they call passive sensors, and the resistance will vary with changes in a condition. So, for example, a coolant temperature sensor, right, on a vehicle that's measuring the engine coolant temperature. As the temperature of the vehicle changes, so will the voltage amount that comes back to the ECU. Then we have other sensors that use a reference voltage, and this is more common in most of our modern vehicles. The computer steps down the battery voltage, usually using what they call a 5-volt reference. That feeds a smooth and consistent power supply to the passive sensor, which in turn we can measure those changes against that basically isolated voltage that we now know as the reference voltage. Here you'll notice that the sensor is fed a 5-volt reference or VREF signal provided to it. And then based on what that sensor is dealing with, whether it's temperature or the resistance is changing because of some factor such as motion, it sends a voltage back. That low voltage is then amplified. It's in an AC format, you can see here, but computers typically want to work with digital signals. So we have to condition that signal's turned from an AC signal to a digital signal. That input is then sent to the microprocessor, the real brains of that computer, and then based on that, it sends out an output request that again goes out as a digital signal, but has to be conditioned back to an AC signal for the component that's going to actually interpret whatever that message is. Now there are variations to this type of process. Some sensors now are actually able to do the digital conditioning up front, so they don't need to be converted later on in the computer, which actually helps us speed up things as well. When we're looking at the active and passive sensors, you'll notice that the variable resistor sensor allows for a change in internal resistance with a change in some kind of condition. Now, that condition could be temperature related, it could be the physical movement of some kind of pedal, for example. And these resistance types of sensors are very common in our vehicles today. We also have what they call switching sensors, another very popular design. And these are just open or closed sensor circuits. So for example, some cars have a secondary air system on them that kicks on when you first start the car when it's cold, and then shuts off once it's warmed up the catalyst. We also have magnetic sensors. These have become probably the most common in modern vehicles, and these use parts of different movements to induce a current to produce a signal for the computer, often referred to as some kind of either magnetic pickup or Hall effect style sensor. And here you'll see that we actually have specific Hall effect sensors that use a semiconductor chip to sense parts and movement. of speed sensors. Now you'll notice we'll find that they have things called crankshaft position sensors that come in both a magnetic style sensor and a Hall effect sensor. And the Hall effect sensors always produce a digital signal, where the magnetic style sensors typically produce an AC style signal. There's also solar sensors. These sensors are used to convert sunlight into electrical signals. These are often used on vehicles that have usually higher end HVAC systems that can actually control the amount of cold air being diverted to one side of the vehicle or the other. And then we have directional sensors, and those detect polarity of a moving magnet, and they are used in some navigation systems. On top of this, some of them don't even use magnets. They literally use something called a yaw rate sensors, which has a special type of crystal that gives off a voltage with pressure movement. Here we see another list of a bunch of specific sensors that are involved, and we have many sensors in automotive. Here you'll see we got intake air temperature sensors and coolant temperature sensors. We've got oxygen sensors and manifold absolute pressure sensors. All of these sensors provide some kind of specific feedback to the computer that in turn can make some kind of decision with its rationale to actually cause some kind of output. Here you can see that our sensor list just continues to grow. We've got crankshaft position sensors and mass airflow, knock sensors, brake switches, all kinds of different sensors. And some of these you may be familiar with, and some you may not be familiar with. And so it's important to kind of take a good look at this list, make sure you're getting familiar. The lingo is used around a shop, so it is important that as technicians, that when we're in a shop atmosphere, we understand what these abbreviations stand for and what we're actually talking about when we're talking about these different sensors. And finally, on our list, and trust me when I say that there's many more of these, we have some additional sensors here related to just different systems on the car. And the amount of sensors that we have on a vehicle today is in the hundreds, right? Easily. There's many different sensors, impact sensors in this case. We got EGR, we talk about vehicle speed sensors, fuel temperature, pressure sensors, all these different inputs going on. So it's no wonder that sometimes, somebody acts up and gives us a problem. We get that weird check engine light or something happening in the car, right? Then we get to some of the computers. And the computers by different manufacturers have all kinds of different names. So here you can see some that are listed: CPU, ECU, ECM, PCM, and it's almost mind-boggling. And I know on some of the German vehicles, for example, they even call it different things, something like an ME. So again, just kind of understand that these are interchangeable languages that we use when we're referring to specific computers on a car. In this picture now, we can see a bunch of the locations of these processors. So keep in mind, there is an engine computer. That's a very popular one, very common. Probably one of the first computers actually incorporated in a car. But there's many other computers. Most vehicles today are being built with about 50 or more computers or ECMs or ECUs on that vehicle that all have a dedicated function within the vehicle. As we look at these different computers and their locations, we also have to understand what are the different computer types that are out there. And there's all kinds of different computers. So we have vehicle control modules that are on there, sometimes referred to as like body control modules. There's powertrain control units, which are going to really function or be related to powertrain components on there. We got engine control modules, right, dealing with the engine stuff. We've got anti-lock brake modules, instrumentation, ignition modules, all these different areas. And you can tell from the names that we didn't get too creative. Most of the time, we name a component after what it's actually in charge of. So each of these, if you look at the anti-lock brake module, yeah, well, guess what? It is dealing with anti-lock brake systems on the vehicle and determining what, based on what inputs it gets, what outputs need to happen. And again, just more computer systems. So we got suspension and climate control, airbags, and high voltage. You can see right here, man, that's just, two sets of control units. But I said there's 50, so they can get really confusing when we're looking at vehicles, trying to determine which ECU is which, because they don't often always have a name stamped on them to tell us what they are or what their function is. Just a little tech tip for everyone, too, so that you know. Computers used to be named black boxes, and you still hear this term on aircraft, and that's because the electronic circuitry was actually enclosed or saturated in a black plastic film inside a metal box, and that's kind of where that nickname came from. Kind of cool when you think about it. All right, so let's start talking about the parts of a computer. So a computer will always have a housing. It's typically made of a metal or plastic enclosure protecting the electronic components. There's also going to be some kind of circuit board inside of this, and some of them will have more than one circuit board. And this is built on some kind of plastic or fiber board insulator that can't conduct electricity. The flat metal conductors are printed and then they're put on the surface, right, that help connect and hold the components in place. And then inside of all of that, we're going to need some kind of way to connect all these little components together. And they'll usually use some kind of harness connector. There will be some kind of multi-pin terminal attached to the vehicle's harness. That's where all of them feed up, where you can actually connect the actual control unit to itself. Think of it very much about like one of your computers at home. It looks like there's going to be some kind of connection where you actually connect the monitor or the keyboard to something, right? Some kind of wiring harness that goes in between the two items. Every computer has to have some kind of clock, and that coordinates, right, exactly how signals are sent through circuits. That keeps everything within sync. Then there's computer memory that stores the data for the microprocessor, sometimes referred to as RAM, right? And then there's volatile and there's non-volatile memories that we need to be aware of. The microprocessor that's in there that's storing the data has to analyze the data from the sensors. And from the sensors, it then needs to compare that data against what they call some kind of good operating value or a map, right? Something that's been mapped in that vehicle to be considered okay. Then it needs to calculate, okay, based on those inputs, what would be the proper command? What do I need to change to correct the data that I'm getting or improve the situation to the desired reaction that's the driver, for example, is giving as an input? The voltage regulator that's built into these systems converts battery and the generator voltage into a lower, cleaner DC voltage. So usually this is termed rectification. Voltage is safely used by ECM circuits so that the dash displays and sensors aren't damaged by an over voltage or under voltage, which can affect what those outputs or inputs might look like. The computer amplifier that's built into it is designed to be there to enhance that signal and strengthens it for different signals inside the computer. So you can take this very micro style signal and convert it into something much stronger that the computer can interpret. Computers also have to have some kind of conditioner, right, or also called a converter or interface. And those alter the signals for use by other chips in the circuit. Those also protect the computer from shorted or ground circuits in case there's a problem. In addition to those two circuit protection devices for these microprocessors, we have a buffer in there. And the buffer is allowed to be able to temporarily be used as a storage area for some of the data, just because we got so many signals moving so fast between each other. The output drivers use a power transistors that are step up the current, right? And those in turn allow us to provide a ground path to actuators to actually perform some kind of operation. You'll notice that the microprocessor operation is very similar to what we've seen before. We have some kind of voltage regulator that gives us a reference voltage to use that in turn it goes to some kind of conditioner or operating input. That input is switched into a low voltage AC system that needs to be amplified and then converted into a digital signal. From the digital signal, the microprocessor can make decisions, it can store it in the memory, and then it can decide based on a bunch of different inputs, hey, what's the best output? That output is sent out, has to be conditioned back to an AC signal in many cases, and then can be sent out to the actual actuator to perform the job function being requested. Next, let's take a look at memory operation. So computers use many different types of memory. The computer memory data stores things as voltage charges, right, or changes actually. The random access memory is our RAM. You probably heard that from your computers at home. We also have ROM, the programmable removable memory, and different other options here that you'll see. Let's take a look at the CAM, or Keep Alive memory. That allows the computer to have an adaptive strategy. And that adaptive strategy happens from the very moment that you start up the vehicle. The car is constantly adapting the fuel-air mixture that's going on in the vehicle. It's needed also as well for parts that wear on the car. We have to adapt for known worn parts. As parts wear down, we can adapt for fuel mixtures and air leakages that are actually occurring as things deteriorate up into the point that they might need replacement. CAM information allows the computer to maintain normal vehicle performance with abnormal inputs from sensors. And that is critical so that vehicles don't totally fail on us. Next, we have the output driver operation that we need to understand a bit about. Sometimes these are referred to as quad drivers. This was very popular. Each area had a certain driver unit, and sometimes on a control unit, one of those drivers would burn out. You could literally see that on the circuit board. The output driver operation is able to control the current flow through the actuators. This control is critical because we don't want to send too much current or too little current. We also want to be able to precisely control where we want those sensors to be. When they're energized, the driver ground actuators actuates the circuit, so we control the ground side. Actuators can then actually move to perform some kind of actuation that's being desired by the ECU. When we look at the actuators, right, these are the output devices that allow the computer to alter operation of other components. Without these, the computers can make decisions, but nothing would actually physically happen. Think about this way. When you put your foot on the brake pedal in your car, you're pushing down on the pedal, in turn activating a switch that a control module decides, hey, you know what? I know what that means, and it in turn turns on the rear brake lights. These output actuators can be found almost anywhere on a vehicle, especially when you think about the variety of them that we have. For example, vans that may have the actual self-opening or closing rear end lids on them. So the actuators actually are classified a little bit different too. We have different actuators around the vehicle. Now, solenoids are probably a common term that you may have heard of before. Solenoids are often what drives up our door locks inside the car. And in those, we have an electromagnet that actually moves a metal core or a plunger. It actually works on magnetism. All of these actually work very similar, although they have different functions. We have a relay as well, and that reacts to a small signal from a computer to control a much higher current. We also have what they call servo motors that are very small DC motor actuators. These motors, sometimes are referred to as stepper motors, are actually the controls that are up in the dashboard of your car. And then we have display devices, which include LED displays to provide information on the dash and for the instrument cluster. So we have all kinds of different actuators within the vehicle. When these actuators, or the computer actually turns on the actuator, it provides the electrical actuator with a ground circuit. So you're going to hear this ground side control terminology, and that means that the control unit, or the computer in this case, always is controlling the actual ground side of the circuit. The current then flows through the actuator to the frame ground to operate it. So on our vehicles, our chassis act as the ground in almost every case. With relays, these are used when we want to control a high current load. For example, when we turn a key in our car, we actually tell the ECU we want to start the vehicle, and that controls this relay that engages the starter. And then in some cases, we use something called a solenoid. These are used to perform tasks, right, that are such as the door locks or the EGR, and even control the engine idling speed. So we have a bunch of different operations of these types of actuators on the vehicle that you can see. Lastly, we have what they call servo motors, and these are can ground the motor control circuit itself. And they turn the motor on or off and reverses the motor operation. This actually can have many different steps in it, hence the name stepper motor, sometimes it can be referred to. But what happens is, as we actuate something, the north and south poles cause this to rotate and lock into one position or the other. And that can actually cause, for example, a vent in the actual dash to close off or open up based on what the input is from the driver on where they want the air diverted. So here's a list of a bunch of specific actuators. You can take a look through here, but we got the ignition coils, fuel injectors. I'm sure many of these you're familiar with, and I don't want to just read out all of these different actuators. It is important, though, that you make a note of all of these, since it is pretty common in every automobile that's out there, and you would want to know that these are what control certain aspects of that vehicle. Now, computer networks are pretty much the norm today on every automobile out there. They're a series of computers that control different systems, but they actually work together to improve the overall vehicle efficiency or every kind of system in the vehicle by reducing a lot of the wiring that was occurring. We saw this during the late 1990s where the wiring was just getting overwhelming in the car. So this allows all the onboard computers to use the feedback data from several systems so that they can share that input. And then the network computers share common parts. They have two wires in most cases. They're able to share the input signals and therefore then determine output signals. And this reduces the wire. The data from the sensors is exchanged to prevent duplication of parts and to actually really reduce that wiring that makes it easier for us as technicians to diagnose problems. With these networking systems, you're going to hear this term called a data bus. What's going on with the data bus? And that is actually referring to the wiring that's used to create this network between the control units. The signals traveling through a data bus are coded. They actually have like an identifier number, which actually is a specific address on where those messages are supposed to go. And the reason for that is that prevents the signals from being processed by the wrong computer number. If we give them a certain number, for example, 2, control units that are looking specifically for that number 2 will actually accept that message being sent. When we're dealing with networks, you're going to hear about a couple of different styles. One's called serial and the other's called parallel. Serial communication uses only one wire to exchange digital data, and the data transfers one piece at a time. Basically, it has to let the highway open up to send the message back and forth. So it can be a little bit slower, and it also is a slightly less reliable because it doesn't have redundancy built into it. When you deal with parallel communication, that involves usually several wires. In most cases today it's 2, and exchanges multiple pieces of data simultaneously, and it's sent on both wires in order to make sure that the message being sent is indeed been validated so that there's no corruption of that data. In this illustration, we can see on the top a serial multiplex communication line. In other words, you can see there's a single digital line that's being transferred, that's moving information across it. On the bottom, you're seeing a parallel circuit, and this one's demonstrating it with 4 wires connected. And on these systems, right, the more lines that we have, we can control more signals that are sent back and forth to control the actuators that need to respond to whatever those inputs are. Now, taking a look at what you know, here's kind of a better, I guess, picture of what's going on. You can see here when we have ECM set up, we have different configurations. The first one we'll talk about is a star configuration. That's where you've got a master control unit in the middle with what they often refer to as slave control units. In this case, there would be 5 slave control units around the outside. And if you look to the right, you'll see what they call a bus configuration. And this is the most common today that you'll see out there. The bus configuration is what we use with CAN data networks. And on the bottom, you'll see a ring configuration where the information has to be transferred in a circular motion between control units. This is very common on some of the fiber optic sound systems that are out there, usually coupled with the star system. So I've already hinted at controller area networks, right, or CAN. These are specific type of high-speed computer data buses that are used. Again, as I mentioned, the most common known today. They've definitely improved and increased the speeds, but CAN you'll still find on a lot of cars. Several computers and sensors can be used on the CAN bus at any given time, and each computer is able to send and receive information and is actually coupled to certain actuators and sensors. So therefore, information from a sensor that's on the front of the car can be transferred to something that's in the back of the car if it's a shared signal. And electronic markers denote the signal's origin. and type of information, and there's a priority system that's used. Again, it's really just the same thing as what you have in your own homes. Everyone has a specific address that the mailman is supposed to be delivering the mail to. So another quick tip, though, to keep everyone just aware of some things to know. In 2008, as of the 2008 model year, all of the diagnostic platforms were now going to be CAN compliant, meaning that any scan tool that you bought would be able to hook up to these various control units. And that's because in order to communicate with those control units, the scan tool actually has to put a message out on that data bus to activate that specific control unit and say, hey, send me the information that you've got going on so that I can send it to the end user. And that's what's displayed on your on your scan tool. Lastly, there was LIN networks, or local interconnect networks. And these data buses were designed to work with the CAN systems. They're suited for sensors and actuators and networking applications, but they're used in just one section, such as an inside door. So it requires what they call a special CAN LIN bridge. The local local interconnect network, or LIN, became popular because it was cost effective. You didn't need to run CAN in every single thing. But for example, if you were to take your door panel off of your car, if it's a new 2008 or newer, you might see one of these LIN networks. They're usually like on this paper ribbon film, and they're designed to really just kind of connect the components in a door at a cost effective method. These single wire conductors were just your basically conventionally insulated wire that carries data signal between the wires as far as the single systems. When you get into the CAN systems and you have the redundant signals, you'll start to see what they call twisted pair conductors. And these are two insulated wires that are wound into a spiral. And that twisting of the wires help cancel out any type of electromagnetic interference. And again, the distortion that happens should be identical and similar if anything was to get around it that was electromagnetic. And the process of this was just to make sure that the control unit could verify that, hey, the message sent to me was indeed what was requested. And these help the computer carry out, faster data processing than single wire conductors that have to wait to send their message. Now, the shielded twisted pair conductor is a metal shield that further reduces electromagnetic interference. You may be familiar with something that looks similar to this. Sometimes a coaxial cable or an antenna cable, if you were to cut it in half, has this tin that wraps around an insulator, and then there's a single wire. Well, they wrap both of the wires with this kind of that metal shielding, and that really helps to reduce even further electromagnetic interference. And they usually are done when they must be used near some kind of high voltage system. So pretty common on hybrid electric vehicles. Then we have what they call differential voltage signal that's used in a twisted pair conductor. Those are two complementary digital signals with opposing polarities, and they are synchronized signals to strengthen low voltage signals between computers. Again, as the vehicles become with components that have higher voltages, there's higher magnetic fields around them. And so we have to kind of protect the integrity of the signal that's being sent. And so that's why you're seeing these different adaptations of those wires. All right, with that being said, I will leave it open for any questions that you may have. Feel free to either send me an email with your questions. We can include this in the Q&A that's in the beginning module that we had, or we can actually bring this up and address it in some of our discussion questions this week. I hope you enjoyed this lecture, and I will see you throughout the week during our discussions, and then we'll be moving on to more and exciting topics in automotive. Thank you, everyone.